Hello there and welcome back to the Sleep Science. Tonight, we're venturing deep into the cosmic ocean, exploring the limits, or perhaps the absence of limits, of the vast universe itself. Imagine yourself gently drifting in darkness, sprinkled with starlight like luminous grains of sand scattered across an endless midnight beach. You peer into the distant reaches, knowing that beyond each star lies more stars, galaxies, and voids, stretching out further than the imagination itself. And tonight, as we float gently on through this celestial landscape, you probably won't survive this. Well, not the existential awe part anyway. But don't worry, physically you'll be just fine tucked safely in your bed. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment below with your location and the local time. Let's see just how far our sleepy science adventure reaches tonight. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Picture infinity. Go ahead, try. You close your eyes trying to visualize it, but your brain politely declines. After all, it's wired for a neat little place called Earth, a place that comes with clear boundaries, oceans, continents, and that spot on your bed reserved exclusively for your cat. You are quite literally wired for finitude, an instinctual love of borders, edges, and endings. Your very cells crave clarity, defined spaces, and comfortable, finite corners to retreat into. But the universe, oh, it has a funny way of teasing us, testing the boundaries of our comprehension. Infinity, you see, is a sly, elusive concept. Humans first grappled with it thousands of years ago, mathematicians and philosophers arguing endlessly about how something without end could possibly exist. The infinite has always danced on the edges of human understanding, always tempting us to grasp it, yet forever slipping through our fingers like cosmic sand. When we talk about space, infinity tends to pop up rather uncomfortably often. Look out into the night sky. Each point of starlight is a distant sun, each with its own collection of planets, moons, and asteroid belts. And beyond those stars, more stars, galaxies, nebulae, and who knows what endlessly outwardly without any clear stopping point. The sheer scope of that can feel overwhelming, a deliciously terrifying cocktail of curiosity, wonder, and existential dread. So what does infinity even mean, practically speaking? Well, it suggests an endless stretching of galaxies outward, no matter how far we look. Imagine riding a spaceship in one direction, traveling as fast and as far as possible, your eyes wide open, waiting, hopping for some definitive endpoint. A sign, perhaps politely saying, "You've reached the edge of everything, kindly turn around." But alas, no sign greets you, just the cold void extending forevermore. Infinity denies us closure, leaving us perpetually hungry for answers. And that's precisely why we struggle so hard against infinity. It's fundamentally anti-human, at least psychologically. Infinity has no neat endings, no tidy conclusions, and certainly no comfortable corners. Historians still argue whether humans instinctively prefer finite environments because they offer security and clarity, or if perhaps our discomfort with infinity arises from something deeper and more philosophical. Regardless, space mocks that desire for clarity. Its silent vastness refuses easy answers and gently whispers, "Keep looking." In everyday life, infinity seems abstract and unreachable. But then again, consider mathematics, our best attempt at making sense of infinity. Mathematicians love playing with this endless notion. They eagerly point out that there are infinitely many numbers between 0 and 1. In fact, between any two numbers, there's an infinite chasm waiting to be explored. Infinity nestled comfortably within finite limits. How's that for messing with your cozy understanding of space and limits? Physicists, too, can't help but dive into this perplexing topic. They've looked outwards into the universe, measuring and calculating, hopping to find edges or boundaries. But as yet, the universe has been frustratingly tight-lipped, revealing no clear edges. If there is a boundary, it's hiding spectacularly well, beyond all our instruments and theoretical insights. The universe simply smiles back, serene in its secrecy. Some astrophysicists hypothesize the universe might be closed, shaped like a sphere or donut, finite yet edgeless, curving gently back onto itself. But others scoff at that idea, suggesting instead that the universe is flat, infinite in all directions, extending forever in a straight line. Your mind struggles at this suggestion, doesn't it? A line stretching forever outward, never curving, never reconnecting, simply going on without end. If your brain is aching slightly from trying to picture this, don't worry. You're in good company. The human mind was not built to grasp infinity. It was built to hunt mammoths, build shelters, and watch cat videos, three activities comfortably limited in their scope. Thinking about infinite space for too long can make your thoughts spin uncontrollably, spiraling outward deeper and deeper into endless contemplation. Luckily, you're comfortably wrapped in blankets, grounded in a reality where the biggest infinite you have to deal with is the endless loop of chores waiting tomorrow. Still, there's a quiet charm hidden in infinity, isn't there? As you lie there breathing softly, eyelids growing heavier, you might even find comfort in infinity's absolute vastness. It means possibilities stretch outward forever, unbounded and unrestricted, a blank canvas waiting to be painted with your imagination's wildest strokes. The universe offers you an endless playground, an infinite horizon, an unlimited expanse of possibilities. And tonight, as your breath settles into a gentle rhythm, let yourself be carried by these infinite possibilities, drifting ever outward into a restful sleep filled with starry dreams and cosmic mysteries yet unsolved. Infinity waits patiently, ready to continue tomorrow night. But tonight, rest easy, floating in peaceful wonder. Long before space telescopes and quantum physics mudded the cosmic waters, humans gazed upward at the night sky with much simpler, yet equally ambitious, ideas about the universe. Imagine you're lying on a grassy hillside somewhere in ancient Mesopotamia, the scent of earth and wildflowers mingling with the distant, comforting warmth of campfires. Above you, the stars drift lazily across the dome of night, and naturally, your thoughts turn skyward, curious, contemplative, and gently bewildered. You have no fancy telescopes, no calculators, not even a pocket-sized star chart app, just your eyes, your imagination, and the stories whispered around campfires and hearths. Yet somehow, humans still manage to paint rich, colorful images of how our universe might look. One of the earliest and most creative cosmological ideas came from ancient Mesopotamian civilizations. They believed our world rested on a vast ocean, cradled beneath an enormous, domed sky. Picture this sky dome stretching smoothly above you, studded with twinkling, tiny lights, holes through which celestial fires blazed. These fires were thought to illuminate the heavens each night, spilling their radiant glow onto the sleeping earth. It was comforting, simple, and poetic, a universe small enough to feel cozy, familiar, and secure. Ancient Egyptians had their own imaginative twist on the cosmos. They believed the earth to be flat, supported, according to some myths, by pillars at its corners. And above this flat earth stretched the body of the goddess Nut, her sparkling gown embedded with stars, her protective embrace gently sheltering humanity. It's a rather elegant image, though you might wonder how those corners looked. Did the Egyptians worry about what happened if one wandered too close to the edge? Perhaps they placed polite signs at the boundaries. Please don't fall off, it's a long way down. In ancient India, the cosmos took an entirely different but equally imaginative form. Hindu cosmology often depicted the universe as resting on the back of 4 giant elephants. And where were these elephants standing, you might ask? Why, on the back of a giant turtle, of course. This charming cosmic stack-up went even further in some traditions, hinting at yet another turtle beneath the first, creating a potentially infinite turtle tower. One can't help but chuckle softly at the thought, turtles, all the way down, though historians still argue whether that phrase originated from actual ancient texts or is simply a modern, humorous reinterpretation. Meanwhile, the ancient Chinese envisioned the cosmos in a gracefully balanced form, a structured and symmetrical place guided by the interplay of yin and yang. For them, the universe mirrored earthly order, with the heavens perfectly matching their ruler's hierarchical realm. It was neat, precise, and satisfyingly organized. A comforting thought as you drift off tonight, your own daily chaos momentarily subdued by celestial symmetry. And then, of course, there were the ancient Greeks, masters of philosophy, mathematics, and some very creative storytelling. Early Greek cosmologies shared similarities with their predecessors, proposing that the Earth was flat and surrounded by a vast cosmic ocean. Picture yourself sailing too far outward, toward that imagined boundary. You might encounter mythical creatures guarding the edge, perhaps politely suggesting you turn back before sailing off into celestial oblivion. For the Greeks, the horizon itself became a tantalizing yet troubling mystery. Where exactly did it end, and what lay beyond? This flat Earth cosmos didn't linger long in Greek thought, however. Soon enough, scholars began to propose a different, more sophisticated idea, a spherical universe, with the Earth neatly centered within nested celestial spheres. Think of it like those Russian nesting dolls, each layer smoothly fitting within the next, forming an elegant cosmic structure. Aristotle himself championed this model, arguing persuasively for a spherical Earth and cosmos. How else, he asked, could we explain the round shadow cast by Earth during lunar eclipses? Aristotle had an annoyingly good point, much to the chagrin of flat Earth enthusiasts everywhere. Even with Aristotle's spherical universe gaining popularity, however, the boundaries of the cosmos remained comfortably finite for many ancients. They imagined outer celestial spheres rotating around Earth, with the stars fixed firmly to their innermost surfaces. Beyond these crystalline spheres, many ancients thought, was the prime mover, the initial cosmic engine setting everything gracefully spinning. Space in this ancient view was neither infinite nor frighteningly endless, but rather tidy, organized, and beautifully bounded. Throughout human history, these diverse ideas offered comfort. A finite universe, with edges or clear celestial domes, provided people a reassuring sense of place, structure, and meaning. You knew your position, your place within a carefully structured cosmic narrative. Even the quirkiest cosmological images had their charm and purpose, reminding humanity of its connectedness to something larger, yet manageably limited in scale. Perhaps the quirkiest fringe cosmology belongs to some ancient Norse traditions, depicting Earth as a flat disk surrounded by a vast cosmic ocean inhabited by monstrous creatures. Jörmungandr, the gigantic serpent, wrapped around the world's edge, biting its own tail. Picture yourself standing on the shore, peering nervously outward into that distant, murky ocean, imagining Jörmungandr quietly circling the edge of reality, patiently waiting for Ragnarok, the world's end, when he'd uncoil dramatically from the ocean's depths. The Norse clearly understood cosmic drama better than most Hollywood screenwriters. But tonight, as you rest gently in bed, nestled safely beneath familiar blankets, think of these ancient visions with gentle appreciation. They remind us that humans have always struggled beautifully, poetically, and imaginatively with the vast unknown above. We've filled that unknown with gods, turtles, elephants, giant snakes, and elegant celestial domes. The ancient cosmos might seem amusingly quirky, even simplistic today, but their creators were simply doing their best to make sense of a universe that was, and remains, far bigger and stranger than we can comfortably comprehend. And just like them, tonight you're safe, snug beneath your covers, feeling the comforting weight of gravity anchoring you to this small, cozy planet drifting quietly beneath the infinite starry skies. Tomorrow, we'll step forward into how humans gently progress toward more nuanced cosmologies, expanding our universe, slowly yet inexorably, toward infinity. But for tonight, let ancient imagination softly lull you deeper into restful dreams, guided gently by celestial turtles, elephants, and mythical creatures at the universe's edge. You're drifting now just a little deeper, the hush of sleep starting to pull at your thoughts, but don't nod off just yet. We're about to meet some ancient Greeks who, quite frankly, took stargazing to a whole new level. While earlier civilizations imagined cosmic turtles and celestial domes, the Greeks had an entirely different idea. What if the cosmos wasn't just big, but elegant? What if space wasn't a haphazard collection of stars scattered randomly, but rather an intricate, beautiful system of spheres, all revolving with divine precision? It's around the 6th century BCE when you bump into Pythagoras. He's not just about triangles, he's also floating the idea that the universe should reflect perfect mathematical harmony. He and his followers believed celestial bodies moved according to musical ratios, creating a music of the spheres that was, tragically, inaudible to mere mortals. Imagine, if you will, the planets twirling around in space to a gentle, inaudible cosmic symphony. No earbuds required. That idea might sound whimsical now, but at the time, it laid the foundation for thinking of the cosmos as ordered and measurable, a giant mathematical machine. A bit later along comes Plato, who insisted that the stars were affixed to the innermost of the celestial spheres, gigantic, transparent layers that wrapped around the earth. He argued that everything in the heavens must move in perfect circles, because circles, to the Greeks, were the ultimate symbol of perfection. Straight lines were just too emotionally unstable, apparently. Then there's Aristotle, forehead furrowed, robes swirling in the Mediterranean breeze, who took these celestial ideas and ran with them. He proposed that the universe was finite but contained within a series of concentric spheres, each carrying the moon, the sun, the planets, and finally the stars, all spinning gracefully around a stationary Earth. And behind all that rotation, a mysterious force he called the prime mover. No, not a workout program. The prime mover was the ultimate cause of cosmic motion, acting without being moved itself. A divine push, if you will. Aristotle's model was clean, satisfying, and deliciously symmetrical. And most importantly, it placed Earth, and by extension, you, at the center of everything. That's the kind of ego boost ancient humanity needed. You weren't just some random speck floating in a meaningless void. You were smack in the middle of the divine dance. The universe literally revolved around you. And this view stuck around for quite a while, centuries, in fact. Even after his death, Aristotle's influence loomed large over astronomy and natural philosophy. His ideas were so well constructed and neatly packaged that challenging them was basically like trying to convince someone today that coffee isn't a necessary food group. Laughable. Now, there was a fringe group of thinkers who quietly disagreed. Around 250 BCE, an astronomer named Aristarchus of Samos proposed something radical. Maybe the Earth wasn't the center. Maybe, just maybe, the Earth moved around the sun. But nobody was really ready to hear that. Poor Aristarchus was more or less ignored, like that one person at a party trying to talk about taxes when everyone else is playing charades. The Ptolemaic model eventually became the cosmic standard. Ptolemy, a 2nd century Alexandrian astronomer, took Aristotle's ideas and added his own mathematical tweaks, creating an impressively complicated system that kept Earth in the center, but included all kinds of little tricks to explain the odd motions of planets. Epicycles, deference, equants. It was the cosmological version of a Rube Goldberg machine. Planets were no longer moving in perfect, simple circles. Instead, they looped and wobbled and backtracked like confused cosmic tourists. But hey, as long as Earth stayed in the center, nobody really complained. Historians still argue whether Ptolemy genuinely believed in his model's physical truth, or just saw it as a useful tool to match observation with expectation. Either way, the Ptolemaic system reigned for over 1,000 years. That's right. Humanity clung to an Earth-centered, sphere-based cosmos for more than a millennium, despite mounting observational oddities. Still, you can't blame them entirely. After all, the sky did look like it revolved around Earth. You watched the stars rise and set each night, saw the sun arc smoothly across the sky, and felt firmly rooted to the solid ground beneath your feet. If anyone told you back then that you were actually spinning through space on a giant rock hurtling around a distant star at tens of thousands of kilometers per hour, you might have stared at them with the same level of suspicion you reserve for online ads offering one weird trick to live forever. But deep down, those ancient thinkers were doing their best. They crafted systems that reflected their observations, their values, and their longing for cosmic harmony. You can almost hear the crackle of torches as they discussed planetary motion under the stars, their robes rustling as they traced imaginary orbits into the night air. And while some of their ideas now seem quaint or wildly off-target, their desire to understand the cosmos, that part hasn't changed one bit. You're still lying awake under the same stars, still asking the same questions, still peeking into the same cosmic abyss and wondering, how far does this really go? So as you sink deeper into sleep, remember that your curiosity links you to an ancient lineage of dreamers and stargazers, people who saw mystery in the night sky and refused to let it go unanswered. Tomorrow night, we'll peek into the moment when all these ancient assumptions were turned on their heads, thanks to a little invention called the telescope. But for now, let the elegance of spinning spheres and silent cosmic music cradle you gently, guiding your thoughts in slow, lazy circles toward a deep and restful slumber. You're gliding now, comfortably nestled in that halfway place between waking thought and drifting dreams, and here, where things start to wobble because someone hands you a telescope. It's the early 1600s and your name for tonight is Galileo Galilei. You've got a strong jaw, an Italian accent, and a slightly rebellious streak that's about to land you in some cosmic hot water. You lift your primitive telescope, essentially just a pair of spectacle lenses in a tube, and point it at the moon. What you see isn't the smooth, divine orb described by Aristotle, but a battered landscape filled with craters, valleys, and mountains. And suddenly, the heavens aren't so perfect anymore. With each adjustment of the lens, you peel back another layer of ancient belief. You turn the telescope toward Jupiter and discover, wait for it, moons. 4 little dots dancing around the gas giant, just doing their own thing, orbiting not Earth but Jupiter. This small discovery delivers a massive shock to the old idea that everything revolves around us. If moons can circle another planet, maybe, just maybe, Earth isn't quite the cosmic VIP we thought it was. Next, you look at Venus and realize it goes through phases like the moon. The only way that makes sense is if Venus is circling the sun, not Earth, which is awkward, considering nearly everyone still believes the Earth is the unshakable center of the universe. You, however, are starting to feel that center slipping. You didn't mean to start a cosmic rebellion, but here we are. Galileo, bless him, starts writing about these discoveries, publishing observations in letters, books, and the occasional cheeky pamphlet. He backs the Copernican model, a sun-centered universe where Earth orbits along with the other planets. And this, unfortunately, puts him squarely at odds with the Catholic Church, which, let's just say, preferred a more Earth-centric narrative. To them, the Copernican system wasn't just wrong, it was dangerous. It suggested that the biblical view of the cosmos might be flawed, and nobody wants to hear that during Sunday brunch. Historians still argue whether Galileo was jailed for his science or his attitude. He was definitely a bit of a provocateur, calling people out, mocking those who clung to outdated models and generally stirring the pot. Either way, he ends up under house arrest, muttering "E per se move," and yet it moves as he's dragged away. That one sentence, whether he actually said it or not, became a rallying cry for science, a whispered defiance against forced ignorance. His work opened the door for a new era in astronomy, one where observation began to outweigh philosophy, and hard evidence started to pry the universe open. And with every improvement in telescope design, the heavens grew more detailed, more intricate, and far less Earth-focused. We discovered that Saturn had rings, that the Milky Way was made of countless stars, and that space wasn't a neat set of concentric spheres. It was vast, messy, and full of motion. Now imagine being alive during that time, when humanity's place in the cosmos was shrinking by the day. First, we weren't at the center of the solar system. Then we weren't even at the center of the galaxy. Soon, we discover that our galaxy was just one among many, millions, maybe billions, swirling out into endless space. No wonder people were starting to lose sleep. It's like being told your hometown isn't the capital of the world, or even of your state, but actually just one quiet neighborhood on the outer edge of a sprawling, unknowable metropolis. This telescopic awakening created a cascade effect. Philosophers began questioning more than just planetary motion. If space was vast and Earth wasn't central, what did that mean about humanity's importance? About our relationship to the divine? About the possibility of life elsewhere? Suddenly, the night sky wasn't a ceiling, it was a frontier. And yet, even with all this expanding knowledge, something in you still wants to find the edge. You lie there in the dark, maybe staring up at the ceiling as if it might pull away and reveal stars, and you wonder, if I kept going, kept moving outward, where would I stop? What would I find? Galileo cracked open the door, but he didn't give us the final answer. He just showed us that our assumptions were fragile, and that reality, inconveniently, doesn't care about how cozy your worldview feels. Here's a quirky twist. Despite how transformative his work was, Galileo never saw more than the tiniest piece of the universe. His telescope could only magnify things about 20 times. Your phone's zoom camera might be better. And yet, those early glances were enough to shatter centuries of cosmic certainty. All it took was a tube, some glass, and a stubborn willingness to look again. So tonight, as you ease deeper into sleep, think of Galileo, his wrinkled hands adjusting the telescope, his eyes squinting toward the stars, his mind whirring through forbidden thoughts. He risked everything to show us we weren't the center, and in doing so helped us see how big everything really is. Not terrifyingly big, not coldly big, just beautifully, unimaginably vast. You're not falling through the sky anymore. You're floating like his discoveries, steadily moving outward, curious, weightless, and just a little rebellious yourself. Tomorrow, we'll meet another thinker who took Galileo's telescope and aimed it at infinity. Sir Isaac Newton, whose gravity didn't just hold apples down but tugged at the entire structure of space itself. But for now, let your mind settle, your breathing slow, and your dreams telescope outward, one gentle revelation at a time. You wake still floating, not with a start but with a slow stretch, like the universe itself exhaling. The stars around you seem quieter now, distant but patient, as if waiting for you to notice something more. It's the 17th century now, and we've moved from telescopes to apple trees. Enter Isaac Newton, mathematician, philosopher, amateur alchemist, and full-time mental overachiever. Picture him under that famously mythologized apple tree. The story goes that one little fruit fell on his head and cracked open the mystery of the universe. More likely, it just bounced nearby. But hey, never let the truth get in the way of a great bedtime story. Here's the thing. Before Newton, gravity wasn't exactly a cosmic concept. Sure, things fell, arrows arced, apples dropped, feet stayed grounded. But nobody had managed to tie it all together with such elegant, terrifying precision. Newton's brilliance was not just in noticing gravity, but in realizing that the same force that tugged the apple to the ground was the very same force holding the moon in orbit around Earth, and Earth around the sun. It was one law, one rule, governing everything from your backyard to the farthest star. That idea, kind of a big deal. Suddenly, space wasn't just a backdrop, it was a system. Newton's laws described how planets moved, how tides rose, how comets flew. His universe was mechanical, orderly, and critically infinite. Yes, infinite. That was Newton's bold leap. He imagined the universe stretching endlessly in every direction, stars sprinkled through an endless void, governed by gravity's invisible hand. You might be wrapped up in a cozy blanket right now, but Newton's universe had no such comfort. It went on forever, with no edges, no boundaries, just infinite repetition. Of course, this raised a few questions, some of them deeply unsettling. If the universe was infinite and filled evenly with stars, shouldn't the night sky be as bright as day? After all, every line of sight should eventually land on a star. This is the start of what would later be called Olber's paradox, but Newton in his time wasn't too troubled by it. He reasoned that stars were far enough apart and their light perhaps hadn't reached us yet. Problem. Not exactly solved, but politely ignored, like that one squeaky floorboard in your childhood home. Historians still argue whether Newton really believed in a spatially infinite universe, or if he simply accepted it as a mathematical necessity, something that made the equations tidy and the models work. Either way, his vision was radically different from everything that came before. It didn't center on Earth. It didn't put humanity in a privileged place. It didn't even require God to constantly turn the gears, though Newton still believed in a divine creator. He just imagined him more like a watchmaker than a puppeteer. Now imagine you're a thinker in Newton's time. You've grown up with a comfortable belief in celestial spheres and divine perfection. Suddenly, this powdered-wig genius comes along and tells you, actually, it's all just masses pulling on other masses across empty space forever. No drama, no crystal orbs, just math. It's enough to make you lie awake at night, staring at the ceiling and wondering if infinity might actually be too big. And that's the thing. Newton's universe was elegant, yes, but also deeply unsettling. There was no edge, no center, no up or down. You floated in it, planet on planet, star next to star, all of it moving according to cold, universal laws. The comfort of Aristotle's concentric spheres had been replaced by the chill of cosmic mathematics. But even in its starkness, there was something strangely beautiful about Newton's cosmos. You could predict planetary motion centuries in advance. You could calculate the fall of an apple and the orbit of the moon using the same formula. Space was no longer just a mystery, it was a mechanism. And that sense of order, of knowability, offered its own kind of comfort. No need for cosmic turtles anymore. Newton also introduced the idea of absolute space, an infinite, invisible stage upon which all matter danced. This space wasn't just empty, it had structure, definition, and direction. It was the canvas of the cosmos, stretching eternally in every direction, unaffected by the events it hosted. It didn't bend, flex, or react. It simply was. At the time, this was radical and oddly calming. Space was predictable, stable, unchanging. Still, even Newton had his cosmic anxieties. He worried that an infinite, evenly populated universe might collapse under its own gravitational pull, every star tugging on every other star forever. Something had to give. His solution: divine intervention. Newton imagined that God occasionally stepped in to reset the universe, giving it a gentle cosmic nudge to prevent everything from falling into a gravitational pileup, a kind of divine maintenance plan. Quirky side note: Newton also dabbled in alchemy, tried to find hidden messages in the Bible, and spent years attempting to calculate the exact date of the apocalypse. So yes, even the greatest minds can go down some strange rabbit holes when left alone with their thoughts for too long. Maybe keep that in mind next time you're 4 Wikipedia links deep at 2 a.m., researching whether black holes can sneeze. But despite his more eccentric interests, Newton laid the groundwork for everything that came after. His laws of motion and gravity were the gold standard of physics for over 200 years. For generations, people believed they finally had the universe figured out. It was big, it was infinite, and it was ruled by clear, rational laws. You could fall asleep under the stars knowing that they moved with predictable grace. Nothing to fear, nothing left to discover. Just eternal equations drifting through eternal space. Of course, as you'll find out soon enough, that sense of certainty wouldn't last. Because the universe, it still had a few surprises in store. For now, though, rest easy under Newton's stars, predictable, infinite, and quietly humming with the pull of gravity. Drift gently on this endless stage, your dreams orbiting soft and slow, like moons circling their silent host. You're floating now in Newton's infinite universe, feeling a little more comfortable with the whole space goes on forever thing. The stars seem orderly, the planets obedient, and gravity's quiet pull gives everything a satisfying rhythm. You could get used to this, drifting through a cosmic ballet, choreographed by equations. But just as you're about to settle into that cozy certainty, the night sky throws you a paradox. A simple, frustrating, and surprisingly persistent question. If the universe is infinite and filled with stars, then why is the night sky dark? This is Olber's paradox, and while it sounds like the title of a mid-tier sci-fi novel, it's actually a deceptively deep cosmological riddle. Named after Heinrich Wilhelm Olbers, a German physician and astronomer with an apparently limitless supply of intellectual curiosity, this little brain twister kept thinkers up at night for centuries. Here's the problem in plain terms. If space is truly infinite and stars are scattered throughout it evenly, then no matter where you look, your line of sight should eventually land on the surface of a star. There should be no gaps. Every tiny patch of sky should be bright. In fact, the night sky should blaze with the brightness of the sun. But it doesn't. Instead, we lie under a blanket of velvet darkness, with stars sprinkled here and there like someone gently shook a bag of glitter over black silk. That darkness is comforting. It feels like night should feel. But under Newton's assumptions, it shouldn't be there at all. Something not adding up. Olbers wasn't the first to notice this, by the way. The question was quietly haunting thinkers long before his name got attached to it. Kepler wondered about it. Halley puzzled over it. Even Edgar Allan Poe mused on the idea in a poetic sort of way. Historians still argue whether Olbers actually offered a meaningful solution or just helped the paradox get its branding moment. But the problem persisted, whispering softly to every stargazer. If infinity is real, where's all the light? Several answers were proposed, some of them inventive. One idea was that interstellar dust blocked the light from distant stars. A nice thought, except dust absorbs light and then re-radiates it as heat, which would still make the night sky glow, just in infrared. Another theory said maybe light from the farthest stars simply hasn't had time to reach us yet. That one was getting warmer, literally and figuratively. You start to realize that maybe the universe isn't old enough for infinite light to arrive. Maybe we're only seeing the stars whose light has had time to travel across space. If that's true, then the observable universe is limited, not because the universe itself has an edge, but because time does. The further you look, the further back in time you see. At some point, you're staring into the deep, starless darkness before stars even existed. That's not empty space, that's cosmic history, unlit and unread. And here's the twist that really stirs your sleepy thoughts. Olber's paradox isn't just about light. It's about infinity and time, about beginnings and visibility. It quietly introduced the idea that the universe might not be infinite in age. That maybe there was a beginning, a starting point, a time before stars. That kind of thinking laid the groundwork for a much bigger cosmic shift. Because it's not just about why the night sky is dark, it's about what that darkness is hiding. It whispers of a universe that's dynamic, not static. One that changes, evolves, maybe even began from something very, very small. But we're not quite there yet. For now, you're still drifting in a universe governed by Newton's laws, staring into a paradox no apple could resolve. Olber's paradox also hints at something deeper, the limits of human perception. We assume that what we see should match what is, but the cosmos doesn't work that way. Just because the universe might be infinite doesn't mean we can see all of it. Light takes time to travel. Stars have lifespans. Space expands. The night sky is a snapshot of a moment, not a final product. And honestly, there's something deeply poetic about that. You're not looking at the universe as it is now, but as it was. The stars you see tonight may have already exploded into supernovae or faded into black dwarfs. The light is old. Some of it is ancient. Some of it has traveled for billions of years just to land softly in your eye tonight, just as you're about to drift off. Cosmic postcards from a distant past. That little voice in your head might whisper, but still, could there be an edge, a place where the stars stop? And that's the kind of question Olber's paradox loves to tangle. If space is infinite, the stars should never stop. If it's not, then where's the wall? And if we can't see all the stars, how can we ever know? You don't need to answer it tonight. Let it float in your mind like a glowing ember, quietly warming your thoughts as you slip deeper into the dark. You're not alone in wondering. Every astronomer, poet, and backyard skywatcher has looked up and asked the same thing. Why does the infinite feel so quiet? Tomorrow, we'll meet someone who dared to suggest that space itself might be curved, not just filled with stars, but fundamentally shaped by gravity and energy. But tonight, stay with Olber's and his quiet paradox. Let the darkness be what it is, not emptiness, but a veil, a sign of how much is still out there, waiting. As you close your eyes, remember, even the most infinite things have their mysteries, and some questions are best carried into dreams. You're not quite sure when the stars stopped looking like holes in a ceiling and started feeling like puzzle pieces. But now they stretch around you, vast and quiet, and you're beginning to realize that maybe space isn't just infinite, maybe it's weird. Which brings us to a certain patent clerk from Switzerland with unruly hair and a knack for asking questions that rearranged reality itself. Tonight, you're floating gently into the realm of Albert Einstein, whose thoughts bent space like a bedsheet and twisted time like a wrung-out towel. Ready? Don't worry. We'll go slowly. It's sleepy science, not a physics final. By the early 1900s, Newton's universe was starting to feel a little too tidy. Yes, gravity explained a lot, but there were cracks in the marble, little inconsistencies in Mercury's orbit, for example, and the growing realization that light didn't play by Newton's rules. Then along came Einstein with his theory of special relativity in 1905, casually suggesting that time and space weren't constants at all, but slippery, flexible things that depend on how fast you're moving. Most people were still recovering from the whole Earth isn't the center of the universe drama, and now this guy was saying time isn't universal. Rude. But the real cosmic earthquake came in 1915 when Einstein dropped his general theory of relativity. In it, he proposed that gravity isn't really a force pulling things together. No, it's something better. He described gravity as the warping of spacetime itself. Picture space as a trampoline. Put a bowling ball in the center, that's a star or a planet. Now roll a marble around the edge and it curves inward, following the fabric's bend. That's what gravity really is, the path an object takes through curved spacetime. This was revolutionary. It meant that space wasn't just a stage where things happened, it was an active participant. It bent, it stretched, it responded. Space itself could warp under the weight of matter and energy, shaping how objects moved and how time flowed. In Einstein's universe, the geometry of space wasn't fixed. It danced in response to what filled it. Historians still argue whether Einstein truly believed the universe was infinite at the time he completed general relativity. In fact, he initially proposed a static universe, unchanging and eternal, because the idea of a dynamic cosmos expanding or contracting was just too messy. To make this work, he inserted a fudge factor into his equations called the cosmological constant, a term designed purely to keep the universe from collapsing under gravity. Later, when it turned out the universe was indeed expanding, more on that soon, Einstein famously called the cosmological constant the biggest blunder of his life. Spoiler: cosmologists would eventually unblunder it, but that's a story for another night. What mattered now was that space itself was no longer passive. It had shape, texture. It could be curved by the things within it, and that curvature told planets how to move, told light how to bend, and hinted at a cosmos that might not stretch infinitely in every direction the way Newton imagined. Suddenly, new possibilities emerged. If space could curve, then maybe it wasn't flat and infinite after all. Maybe the universe was like the surface of a sphere, finite in area but without edges. You could travel in a straight line forever and eventually end up back where you started, just like an ant crawling along a globe. No borders, no walls, just seamless continuity. That idea may soothe your edge-hunting brain a little. Yes, the universe might be finite, but it doesn't need an edge to be complete. Of course, you can't see this curvature easily. Space is huge, and its curves are subtle over vast distances. But gravity reveals the bending. One of the first proofs of general relativity came in 1919 when astronomers observed starlight bending around the sun during a solar eclipse, exactly as Einstein had predicted. It was a moment of pure cosmic mic drop. The headlines the next day hailed him as a genius, though the man himself seemed more annoyed that people finally noticed him just because of a solar alignment. And then there's the matter of time. In Einstein's universe, time and space are part of the same fabric, spacetime, and mass doesn't just warp space, it warps time too. Clocks tick slower near heavy masses. That's not science fiction, it's GPS fact. The satellites orbiting above your head right now have to account for time dilation, or your map app would be sending you into rivers. This bending of time and space means the shape of the universe isn't just a philosophical question. It's physical, measurable, and deeply tied to how light travels, how matter moves, and whether the cosmos wraps in on itself like a four-dimensional pretzel. Some fringe thinkers have proposed toroidal universes. Yes, that's right, the universe shaped like a cosmic donut. Deliciously strange. Historians still argue whether such topologies are physically viable, or just the mathematical equivalent of doodling with equations. Either way, it makes your midnight snack feel suddenly relevant. Now, as you lie there under blankets and starlight, you might wonder, what does all this mean for the edge of the universe? In Einstein's framework, space doesn't need an edge to be boundless. If it curves back on itself like a balloon's surface, then you can travel forever without ever reaching a wall. It's not that the universe ends, It's that direction folds in on itself, like a dream where every road leads somewhere familiar, just slightly stranger each time. You might feel the stretch of that idea in your mind, a gentle pressure like your thoughts trying to warp themselves around this new geometry. Let them. You don't need to master relativity tonight. Just know that the universe is more flexible than we once thought. It breathes, it bends, and it holds you gently in a soft web of gravitational connection. Even now, you're riding the curves of spacetime, slowly orbiting the center of your own quiet night. Tomorrow, we'll dive into a theory so bold it dared to ask, what if the universe actually had a beginning? But for now, let Einstein's vision wrap around you, curved, weightless, and timeless, as you slip into dreams shaped by a cosmos with no edges and no end, only endless motion. You drift now through a universe that's not just curved but conscious of its own complexity. Time flows slower in valleys of gravity. Light bends like a whisper around massive stars, and the edge you're searching for has become suspiciously absent. It's the early 20th century, and the cozy illusion of a static, eternal universe is about to be popped like a soap bubble. Because right here, in a mountaintop observatory in California, a man named Edwin Hubble is quietly shattering everything we thought we knew. Picture it, 1929, Mount Wilson. Hubble, pipe in hand, eyes squinting through a state-of-the-art telescope. He's not just stargazing, he's measuring. Specifically, he's comparing the distance to galaxies with the way their light shifts toward the red end of the spectrum. What he finds is astonishing. The farther away a galaxy is, the faster it seems to be moving away from us. That redshift isn't just a visual oddity, it's evidence of velocity, of motion. Galaxies aren't staying put, they're sprinting away. The entire universe is expanding. This was not what anyone expected. The prevailing assumption was that the cosmos, like a nice library, was stately and serene. But here was Hubble, essentially telling us the shelves were sliding apart, the bookshelves were zooming off into the distance. Space itself was growing. And here, where things get really wild, if space is expanding, then logically it must have been smaller in the past, much smaller. In fact, roll the cosmic clock backward far enough and all that matter and energy was once packed into an unimaginably dense point. A singularity, a beginning. Cue the drama. The Big Bang wasn't some fiery explosion from a point in space. It was space, stretching and expanding from an original moment. The start of everything, even time. You probably won't survive this idea either, at least not without your brain doing a slow somersault. The Big Bang theory didn't land easily, by the way. In fact, when it was first proposed by Georges Lemaitre, a Belgian priest and physicist, some dismissed it as suspiciously theological. Historians still argue whether Lemaitre's religious background influenced his thinking, or if he simply followed the equations wherever they led. Either way, the math didn't lie. Einstein himself initially resisted the idea, preferring a steady-state universe. He even called the expansion model abominable. But when he saw Hubble's data, let's just say he raised an eyebrow and adjusted his equations accordingly. This expanding universe has no center, by the way, at least not in the way you might imagine. Every point in space is moving away from every other point, like raisins in a rising loaf of bread. If you're lying in the dough, which, let's be honest, sounds comfortable, all the other raisins seem to be moving away from you. But that doesn't mean you're at the center. It just means space itself is stretching between all things. There's no privileged viewpoint, no anchor. Just a universe growing steadily larger, quietly increasing the distance between everything. And this naturally raises new questions. If the universe has been expanding for billions of years, is there a limit to how far it can stretch? Does it go on forever? Or is it more like the surface of a balloon, finite yet edgeless? The Big Bang doesn't answer this. It only tells us that space had a beginning, not that it necessarily has an outer boundary. The edge you're looking for might not be a cliff or a wall, but a limit in time, a cosmic horizon past which light hasn't had time to reach us. Here's a quirky tidbit. The term Big Bang was actually coined by Fred Hoyle, a critic of the theory, during a BBC radio broadcast. He meant it mockingly, but the name stuck. It's ironic, really. Hoyle was a proponent of the steady-state theory, which held that the universe was eternal and unchanging, with new matter constantly appearing to fill the expanding space. It was a tidy solution, but the evidence kept piling up in favor of a singular beginning, most notably the faint afterglow of creation itself, the cosmic microwave background. But that discovery is still a night away. Tonight, you're floating in a universe that's not just big, it's growing. Every second, the space between galaxies stretches a little more, like breath slowly filling a lung. The stars above you aren't fixed in place. They're receding gently, constantly, quietly. And while this idea might feel disorienting at first, there's a strange comfort in it too. You're part of a living cosmos, a universe in motion, always becoming. Think of it like this. If the universe had a beginning, then every point in space is equally old. You're not late to the party. You are the party. And no matter how far you travel, you're still within the same expanding fabric. No walls, no edges, just more space unfolding. Of course, not everyone finds comfort in an ever-growing universe. Some look at expansion and wonder if there's a final destination, a stopping point. Will it keep stretching forever? Will it slow and contract? Or will it just fade? These are big questions, and we'll gently unravel them in time. For now, just rest in the knowledge that you're floating on a cosmic current billions of years in the making, drifting outward with everything else, part of the same breath the universe exhaled at the very beginning. So lie back. Let the idea of expansion wash over you. No bangs, no noise, just the silent swell of space unfolding, soft and endless, like a lullaby written in light years. You're floating now through something softer than gravity and deeper than time, a universe that breathes. You've left behind the ancient heavens, the ticking Newtonian cosmos, and even Einstein's warping curves. Now, you're drifting through something stranger, an ever-expanding universe, where every second adds more space between you and everything else. And it's all thanks to one man's quiet observations from a California mountaintop. But as you continue outward, gently, dreamily, you realize something important. Not only is the universe growing, it's doing so faster and faster. We return again to Edwin Hubble and his famous law, the idea that galaxies recede from each other at speeds proportional to their distances. The further away a galaxy is, the faster it's moving. This expansion wasn't a side effect, it was the whole show. But for decades, scientists thought the expansion might be slowing down, like a tossed ball reaching the top of its arc. Gravity, after all, is a party pooper. Given enough time, it should tug at all that flying matter and eventually slow the whole thing down, maybe even reverse it. That's what astronomers expected. Slowing, maybe a future crunch or at least a gentle coast. But in the late 1990s, two independent teams of researchers decided to test this idea using Type Ia supernovae, stellar explosions that act like cosmic candles, burning with a known brightness. By comparing their actual brightness to how bright they appear, scientists could measure their distance. And by comparing that to their redshift, they could figure out how fast those galaxies were moving. And then, surprise, the supernovae were dimmer than expected. That meant they were farther away than they should have been, which could only mean one thing: the universe wasn't slowing down, it was speeding up, expanding faster, like someone had stepped on the cosmic gas pedal without telling anyone. Cue the existential blinking. This discovery changed everything. The force responsible for this unexpected acceleration was dubbed dark energy. And if that name sounds vague, it's because we still have no idea what it is. Not a clue. It's not the same as dark matter, which will cozy up to another night, and it doesn't behave like anything else we've ever encountered. It's not a force in the traditional sense like gravity or electromagnetism. It doesn't push in the usual way. It just exists, embedded in space itself, urging the universe to expand ever more quickly. Historians still argue whether dark energy is truly a new thing, or simply a property of spacetime that Einstein almost discovered a century earlier with his cosmological constant. Remember that. The biggest blunder of his life. Turns out, it might have been more like a premature light bulb. What Einstein added to keep the universe from collapsing could actually explain why it's flying apart. Currently, dark energy makes up about 68% of the entire universe. Imagine that. Nearly 70% of everything around you, everything in existence, is something we can't see, measure directly, or understand. We only know it's there because of how it makes the cosmos misbehave. And it's not done. The more space there is, the more dark energy there is because, unlike regular matter, it doesn't dilute as space grows. It stays constant per unit of volume. So the more the universe expands, the more dark energy exists, which makes the expansion faster, which creates more space, which makes more dark energy, and so on. It's like a cosmic feedback loop with a caffeine problem. The implication that the expansion of the universe will not only continue, but accelerate indefinitely. Galaxies that are visible to us today may eventually slip out of reach, not because they've moved, but because space has grown so much that their light can no longer make the journey. The night sky, over unimaginable stretches of time, will grow lonelier. Stars will vanish, not from existence, but from sight. Here's a quiet thought to tuck under your pillow. The cosmic horizon, the limit of what we can observe, is always changing. As the universe expands, it pushes things past that line, not because they cease to exist, but because their light can no longer catch up. There may be parts of the universe that were once visible, but are now lost to us forever. And there may be galaxies just now blinking into view, their ancient light finally reaching us after billions of years on the road. You lie there feeling very small but not insignificant. The universe isn't leaving you behind, it's just doing what it's always done: change, grow, evolve. And you, bundled beneath the stars, are a tiny witness to that cosmic drama. Even stranger is the idea that we live in a dark energy-dominated era. This wasn't always the case. In the early universe, matter had the upper hand. Galaxies formed, stars were born, and gravity was in charge. But now, gravity is losing. Dark energy is taking over. And that shift marks a turning point in the universe's life. One we happen to be witnessing, like opening your curtains just in time to see the tide turn. A fringe but oddly compelling theory suggests that this accelerating expansion could eventually rip everything apart: galaxies, stars, planets, even atoms, in an event ominously dubbed the Big Rip. Now, don't panic. This wouldn't happen for trillions of years, assuming it happens at all. Historians of science still debate whether the evidence truly supports this outcome, or whether the universe will simply coast into a quiet, ever-expanding chill. So is there an edge to space? Not in the usual sense. There's a limit to what we can see, yes, a horizon created by the speed of light and the age of the universe. But beyond that, more space, more galaxies, more unknowable wonders. Expansion doesn't need walls, it just keeps going. Tonight, as you rest, feel the quiet tug of that truth. You are not falling. You are floating on a current of dark energy, carried gently through an expanding cosmos that continues to stretch and sigh, like a great exhale that never ends. You don't need to understand every equation or solve every mystery. Just lie back, breathe in, and let the gentle pull of a speeding universe rock you into sleep. You're further out now than ever before, drifting through the long exhale of the universe. The stars behind you are dimming, receding, growing cold in the distance. But just as the vastness begins to feel a little too quiet, the universe offers you a whisper, a faint, ancient glow stretched thin by billions of years. It's not the light of stars. It's older, deeper. It's the echo of the beginning itself. Tonight, you're wrapped in the cosmic microwave background, the baby picture of the universe, and one of the clearest clues we have about its origins. Imagine the universe as a newborn, not a fireball, not a bang, but a dense, hot fog, a glowing plasma soup where atoms couldn't even form, where light itself was trapped, bouncing endlessly off free-floating electrons like a room with no exits. That was the state of things for hundreds of thousands of years after the Big Bang. Light existed, yes, but it couldn't travel freely. It was stuck inside the cosmic equivalent of a very sweaty blanket fort. Then, roughly 380,000 years after the Big Bang, everything changed. The universe had expanded and cooled just enough for protons and electrons to finally form stable hydrogen atoms. This moment, known as recombination, allowed light to decouple from matter. Suddenly, photons were free to roam, and they've been traveling ever since, stretching across the universe, cooling, redshifting with expansion, until they reached us in the form of faint microwave radiation. This ancient light was first detected by accident in 1964 by Arno Penzias and Robert Wilson, two scientists just trying to eliminate static from their radio antenna. They kept hearing a low, persistent hiss. They tried cleaning pigeon droppings out of the dish, true story, thinking maybe birds were the culprit. But the noise didn't go away. Turns out, it was the universe itself calling, an unbroken signal from the edge of time. That hiss was the cosmic microwave background, CMB, still glowing softly from every direction in the sky. The CMB is surprisingly uniform. It bathes the universe at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. But it's not perfectly smooth. Tiny fluctuations in this microwave glow, barely 1 part in 100,000, represent the earliest seeds of structure, the beginnings of galaxies, of clusters, of everything. These slight differences in temperature are like fossilized fingerprints from the dawn of creation. And with the help of satellites like COBE, WMAP, and Planck, we've mapped them in exquisite detail. Those maps are beautiful, by the way, splotches of red and blue, like a weather report from the edge of time. They tell us more than just where matter began to clump. They also tell us about the shape of the universe, its age, its contents, and even its fate. Based on the geometry encoded in the CMB, scientists have concluded something profound. The universe appears to be flat. Not flat like a pancake, but flat in the geometric sense, no large-scale curvature. What does that mean? Well, imagine shooting two beams of light perfectly parallel to each other. In a flat universe, those beams will never converge or diverge. They'll keep running side by side forever. In a curved universe, though, they might bend toward each other like lines on a sphere or drift apart like paths on a saddle. The CMB tells us that, on a cosmic scale, space isn't curving noticeably in either direction. It just stretches. Historians still argue whether this apparent flatness implies the universe is truly infinite or just really, really big. After all, the surface of Earth feels flat when you're standing on it, but zoom out far enough and that illusion breaks. It could be the same with space. We may simply not be able to detect its curvature yet, but based on all available data, the simplest model fits best. A flat, expanding universe, likely infinite, with no edge in sight. Of course, this doesn't stop the fringe theories. Some physicists propose that what we think of as a flat universe is actually the three-dimensional skin of a four-dimensional shape. Others wonder whether the observable universe is just a tiny bubble in a vast multiversal foam. More on that wild idea later. But tonight, the takeaway is this. The universe is old, uniform, and surprisingly smooth, like a well-worn bedsheet pulled tight across a cosmic mattress. Here's a fun thought to lull you deeper. Every time you turn on an old TV and see static on a dead channel, about 1% of that fuzz is the leftover glow of the Big Bang. That's right. You're casually bathing in ancient radiation every time your electronics misbehave. Cosmic background noise. Literally. So if you were looking for a message from the edge, this might be it. Not a wall or a boundary, but a soft hum stretched thin across time, whispering that everything once came from the same point, the same heat, the same breath. There's something comforting in that. You're not drifting alone through endless darkness. You're cradled in a glow that touches every atom, that once filled every corner, that still lingers in the quiet spaces between stars. As your thoughts slow, picture that microwave background like a warm blanket wrapped around the entire universe. Not burning, not blinding, just present. Just enough to remind you that space had a beginning, and that beginning left fingerprints. Tomorrow, we'll tiptoe into the wilder corners of theory, where physicists whisper about parallel universes and the possibility that ours is just one bubble in a cosmic sea. But for now, close your eyes. Let the ancient light wash over you. The night may be dark, but it's not empty. It's glowing quietly with memories of the beginning. You stir softly now, adrift in a universe glowing faintly with ancient light. The cosmic microwave background hums around you, a lullaby from the beginning of time, but even that subtle radiance fades the further out you float. And somewhere beyond the comfortable certainty of our own observable universe, whispers begin to stir, echoes of other realms, other possibilities. Tonight, you cross into speculative space where the theories are bold, the math gets weird, and the boundaries of imagination blur with the edges of reality. You're stepping, quietly, into the multiverse. It starts innocently enough with a problem called inflation. Not the economic kind, although both can make your head spin, but cosmic inflation, a theory developed in the early 1980s to explain why the universe looks so uniform in every direction. The idea is that, a tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Not just fast, ridiculously fast, like stretching a speck of dust to the size of a galaxy in a blink. This inflationary burst would have smoothed out any wrinkles in the early universe, explaining why the cosmic microwave background is so uniform. But here's the twist. Some versions of inflation don't stop everywhere at once. Instead, they keep going in different regions, creating endless pockets where inflation ends and a new universe begins. These bubbles form, grow, and drift apart, each with its own physical laws, its own constants, its own version of space and time. That's one version of the multiverse, the idea that our universe is just one bubble in a frothy cosmic bath. Quirky as it sounds, this eternal inflation model is taken seriously by many cosmologists. It doesn't just explain the smoothness of space. It helps make sense of certain quantum quirks and strange mathematical coincidences. Historians still argue whether the multiverse is a necessary consequence of inflation theory or an unnecessary leap into speculative fiction. Either way, it's given scientists and sci-fi writers alike a lot to dream about. In some versions of the multiverse, the laws of physics vary from one universe to the next. Imagine a bubble where gravity is twice as strong, or where light travels backwards, or where cats rule everything and you're just their incredibly obedient but strangely hairless pet. The possibilities are endless and mostly completely untestable. That's the frustrating beauty of it. The multiverse offers a kind of cosmic escape hatch, an explanation for why our universe has the particular properties it does. Because if there are infinite universes, then ours is simply one where the conditions were just right for stars, planets, and late-night science podcasts. Some physicists love this idea. Others roll their eyes, because while the multiverse solves a lot of philosophical and theoretical problems, it creates a big one for science. How do you prove it? If other universes are forever beyond our cosmic horizon, cut off from us not by distance but by the very fabric of space, then how can we ever test for them? Science, after all, is supposed to be observable, falsifiable, grounded in evidence. And the multiverse? Well, it's more of a cosmic shrug. Maybe everything that can happen does happen, somewhere. Still, certain fringe proposals dare to suggest that we might be able to detect other universes, not by seeing them directly, but by spotting their fingerprints. Some theorists believe that if two universes collided in the early days of inflation, the collision might have left a bruise in our cosmic microwave background, a cold or hot spot, some pattern not explained by standard models. Teams have scanned the sky for these anomalies. They've found a few suspicious areas, nothing conclusive. But the hunt continues. Here, where things get even more fun, quantum mechanics, the unruly sibling of physics, offers its own take on the multiverse. According to the many worlds interpretation, every quantum decision, every flip of a subatomic coin spawns a new universe. You turn left instead of right, new timeline. You eat toast instead of cereal, another universe. You clicked on this sleepy science video instead of scrolling through memes. Congratulations, you've branched off into your very own personal bubble of soft astrophysical inquiry. It's a little silly, a little thrilling, and entirely unprovable for now. But this quantum multiverse isn't the same as the inflationary one. It's not about spatially separate universes, but overlapping realities, existing in a kind of mathematical superposition. If that hurts your brain a little, don't worry. You're not alone. Even the physicists who work on this stuff sometimes admit they're mostly doing it for the equations. Still, there's something poetic in the thought that perhaps the universe is not just bigger than we know, but infinitely layered. That you are, in some sense, part of a branching cosmos where every possibility unfolds. In one universe, you're already asleep. In another, you're still lying there, wondering what dark energy tastes like. Licorice, probably. And in this one, right here, you're suspended between science and speculation, between the steady pulse of cosmic expansion and the wild flutter of quantum theory. You don't need to choose which version is real. For now, just let the possibility of multiverses drift softly through your thoughts. There may never be a telescope powerful enough to peer into another universe, but there are patterns, subtle, mathematical, and mysterious, that suggest we might not be alone. Not in the alien sense, but in the structural one. Our universe could be one face in a cosmic hall of mirrors, each reflection slightly different, each bubble drifting through its own spacetime sea. So rest easy tonight in your own bubble. You don't need to explore them all. Just this one is miracle enough. One universe, one cozy corner of infinity, one moment to breathe in the vast, exhilarating possibility that we are part of something larger than we can ever fully grasp. Tomorrow, we'll return to our own universe and try to answer a deceptively simple question. What shape is it really? But for now, let the bubbles rise around you, soft and silent, floating through endless space. You're drifting now through an infinite sea of cosmic bubbles, the echoes of parallel universes fading into silence behind you. But even as the multiverse blurs like the tail end of a dream, one question begins to rise gently in your mind like a balloon in low gravity. What shape is all this, really? If space stretches, curves, expands, if it has no edge but still bends back on itself, what does that actually look like? Tonight, we're gliding across the geometry of the universe itself, where space isn't just a backdrop, but a shapeshifter with personality, drama, and a flair for cosmic illusion. Let's start simply with your favorite childhood toy, the balloon. Imagine inflating one slowly. Now draw a little ant on the surface. The ant walks in a straight line, never turning, and eventually, surprise, ends up right where it started. That's a two-dimensional analogy for a curved surface with no edges. The ant never hits a wall, never finds a cliff. The balloon's surface is finite in area but with no boundaries. Now imagine that balloon with one more spatial dimension, and you're on your way to understanding what a closed universe could be like. Finite, curving back on itself, but with no edge to fall off of. Now switch it up. Instead of a balloon, picture an infinite flat sheet, like a tablecloth that never ends. You could walk forever in a straight line and never return to your starting point because there's no curvature, no wrapping. This is a flat universe, the kind that most current evidence, including data from the cosmic microwave background, strongly supports. It doesn't mean the universe is simple or boring. It just means, on a grand scale, space isn't curving toward or away from itself. It's behaving reasonably. Then there's the wilder option, the open universe shaped like a saddle. Picture a Pringles chip stretched into infinity. In this model, parallel lines gradually diverge, and geometry starts acting like it's had a little too much coffee. Triangles don't add up to 180 degrees. Circles expand faster than you'd expect. It's exotic, beautiful, and just a tad unsettling, like a Salvador Dali painting made of math. So which one are we living in? Observational data tells us the universe is astonishingly close to flat. But flat doesn't always mean infinite. It could be a very large loop, or a complex repeating structure that only appears flat within the tiny piece we can observe. Historians still argue whether the current measurements are accurate enough to rule out small curvatures or strange topologies. Space might be playing tricks on us, showing just enough of itself to leave us guessing. There's also the possibility of more playful geometries. Mathematicians have explored toroidal universes shaped like donuts, or 3D spaces with interconnected paths. In some models, if you looked far enough in one direction, you'd see the back of your own head after the light had wrapped all the way around the universe. Wild, right? No, this doesn't mean the universe is a cosmic bakery item. But yes, some physicists casually refer to it as a space donut when the coffee kicks in. The idea that space could loop or repeat opens doors to some heady ideas. If you saw a galaxy in two directions, could it be the same one? Could you meet a second version of Earth? And if you did, would they also be lying in bed, listening to sleepy science about the shape of the cosmos? It's not just theory either. Astrophysicists have looked for repeating patterns in the cosmic microwave background that might hint at a wrapped universe. So far, nothing definitive, but some weird anomalies have appeared, strange alignments, large-scale temperature differences. Fringe theorists have taken these as clues that we're living in a finite, multi-connected cosmos. Most scientists are more cautious, chalking it up to noise in the data or statistical flukes. But still, the possibility hums softly in the background. And then there's topology, the study of how shapes connect. You don't need sharp edges to have structure. Space could be warped in a way that makes it finite but unbounded. Picture a video game level that loops endlessly as you walk off-screen, space like that. Looping not because there's a wall, but because the connections lead you back to where you began. It's a favorite among theorists because it allows for mind-bending possibilities without requiring infinite mass or volume. Here's a quirky little historical tidbit to sleep on. The ancient Greeks, who first seriously considered spherical Earth and heavens, also puzzled over whether space must be infinite. Aristotle thought the universe couldn't go on forever because actual infinities just felt wrong, unbalanced, untidy. Others disagreed. Some early thinkers toyed with the idea of a bounded but unending cosmos, proving once again that even 2,000 years ago, people lay awake wondering about the same things you are now. Modern cosmology, for all its precision, still doesn't have a final answer. We know the observable universe is about 93 billion light-years across, and we can measure its curvature with exquisite detail. But the full picture may be far stranger. It could be infinite. It could be finite and looping. It could be a four-dimensional hypersphere wrapped in dark energy and quietly giggling at our attempts to map it with telescopes. So where's the edge, you ask? Maybe there isn't one. Maybe there never was. If the universe is flat and infinite, there's no boundary to cross. If it's curved and finite, you could travel forever and never find an end. Space doesn't stop, it just is. A seamless, stitched-together something that keeps moving outward or inward or not at all, depending on how you look. But don't let that disorient you. Let it relax you. You don't have to reach the edge. You're already inside the shape of space, held within its invisible folds, curled gently within a geometry that keeps on going whether you understand it or not. You don't need a map when the landscape is everywhere. So tonight, stretch your thoughts in every direction, up, out, across time and distance. Let them loop and drift like light in a curved cosmos. Whether we live in a saddle, a sphere, or a donut, your place in the universe is secure, floating in a shape that holds you close, even if you never quite see its edges. You're floating now in a universe that may be flat, curved, looped, or twisted, but one thing is certain. You've never seen all of it, not even close. Because no matter how powerful our telescopes become or how long we stare into the void, there's always a limit, a cosmic horizon, beyond which we cannot see. Tonight we approach that invisible boundary, not a wall, not an edge, but a limit imposed by something simple and inescapable, the speed of light. Light is fast, about 300,000 kilometers per second fast, but it's not instant. And space is huge. So when you look at distant galaxies, you're not seeing them as they are now. You're seeing them as they were. Light takes time to reach you. A star 1,000 light-years away is showing you a 1,000-year-old image. The Andromeda Galaxy. You're looking 2.5 million years into the past. And when you peer toward the edge of the observable universe, you're seeing light that's traveled over 13.8 billion years. Light that left its source not long after the universe itself was born. But here, where things get strange, you think that means the edge of the observable universe is 13.8 billion light-years away, right? Logical enough. But space has been expanding while that light was traveling. The actual distance to those ancient sources, right now, is more like 46 billion light-years in any direction. So the diameter of the observable universe is roughly 93 billion light-years across. That's the cosmic bubble we live in. Not because there's a border, but because light hasn't had enough time to reach us from beyond it. This horizon isn't physical. You wouldn't crash into it in a spaceship. It's a limit of time and motion, a gentle reminder that no matter how much we see, there's more that remains hidden, not by barriers, but by distance and the relentless rules of physics. And every second that horizon is moving, the universe expands, light travels, the bubble shifts. Some galaxies slip beyond it forever, their light stretched so far by the expansion of space that it will never reach us, no matter how long we wait. Historians still argue whether this means those galaxies are gone to us, or if they still exist in some timeless sense, just forever invisible. Some physicists argue that our cosmic horizon is like a curtain that keeps getting tugged outward, revealing new parts of the universe. Until, one day, there's nothing more to reveal because the light from those distant places will simply never catch up. It's humbling. The observable universe is not the universe. It's just the part we can see. There may be regions far beyond our horizon with stars, planets, and even civilizations. But if their light hasn't reached us yet, we may never know. It's like living inside a vast, foggy forest where the trees only become visible as you walk toward them, and beyond that, silence. There's a quirky, somewhat disturbing side effect of this expanding horizon. Objects we can see now may eventually disappear from view. Their light, once visible, can be stretched beyond the range of detection. In billions of years, future observers might look at the sky and see nothing but a small cluster of nearby galaxies, all others erased by cosmic expansion. The universe, for them, will appear lonely and still. They might never know the sky was once full of light. And that's the paradox of it all. The more we understand, the more we realize we'll never see everything. Our cosmic horizon is a trick of timing. It has nothing to do with distance and everything to do with causality. What we can see is determined not just by how far away something is, but by when its light began the journey, and whether the universe expanded too fast for that light to ever catch us. This can be a little existential if you think about it too hard, so let's slow down. Close your eyes for a moment, just in your mind, and imagine a soft sphere surrounding you. It stretches 46 billion light-years in every direction. Beyond it, the universe continues, but you don't know what's there. Maybe more galaxies, maybe something wildly different, maybe nothing at all. That horizon isn't keeping you in. It's not a prison. It's a boundary of knowledge, not existence. Tomorrow, we'll explore what might lie beyond that invisible curtain, dark energy, voids, the fate of space itself. But for now, you're here, inside the known. Safe in your corner of infinity, surrounded by ancient starlight and gently expanding darkness. You're part of a visible story with an invisible margin. A story still being told, one photon at a time. So rest now, knowing that what you can't see isn't a threat, it's a promise. A promise that the universe still holds mysteries, still hides its deepest truths beyond the reach of light. And maybe, just maybe, it always will. The night feels heavier now, but in a comforting way, like a weighted blanket woven from galaxies, distance, and quiet questions. You're lying just beneath the observable sky, peering past the cosmic horizon into places no light has reached you from. And tonight, we turn toward something stranger still. Something that doesn't shine, doesn't clump like matter, and doesn't behave like anything we've ever touched. Tonight, you float through the mystery of dark energy, the invisible force that's not only pushing the universe apart, but doing it with the kind of passive-aggressive persistence that even gravity can't stop. Let's rewind for a moment. You remember Hubble's discovery that the universe is expanding. Then much later, astronomers expected that expansion to slow over time as galaxies tugged at each other. But instead, we discovered it speeding up. Not just coasting, accelerating. That's when dark energy entered the scene, like an unexpected guest who showed up late to the party and quietly took over the entire room. We call it dark, not because it's ominous, but because we have absolutely no idea what it is. It doesn't emit light, doesn't absorb it, doesn't interact with matter in any way that we can directly measure. But it's definitely doing something. Its fingerprints are smeared all over the large-scale structure of the cosmos, subtly stretching space, pulling galaxies apart faster and faster. According to our current models, dark energy makes up about 68% of the total content of the universe. You heard that right. Nearly 3/4 of everything is made of something we can't see or understand. There are theories, of course. One popular idea is that dark energy is a property of space itself. That is, the vacuum of space, what we usually think of as nothing, has its own intrinsic energy. As space expands, there's more vacuum and therefore more dark energy. That's wild enough. But it gets weirder. Unlike regular matter, which gets diluted as space expands, dark energy remains constant per unit of volume. So as the universe grows, it doesn't thin out, it amplifies. This leads to a kind of feedback loop. More space equals more dark energy, which equals faster expansion, which makes more space, and on it goes. It's like space is running from itself and somehow getting stronger with every step. And gravity, Poor gravity's trying to pull things together, but it's like fighting a tide with a spoon. Historians still argue whether this accelerating expansion means the universe is destined for a cold, lonely future, or if some unknown twist will shift the story again. The most widely accepted view is that if dark energy continues doing what it's doing, the universe will end not in a bang or a crunch, but in a gradual unraveling, a fate known as heat death. But let's not rush there just yet. There are other options, quirkier ones. One such idea is that dark energy isn't constant. It could be changing over time. If it strengthens too much, it might lead to the Big Rip, a theoretical apocalypse where space expands so rapidly that galaxies, stars, planets, and eventually atoms themselves are torn apart. Imagine your molecules slowly drifting away from each other, like a dream being unstitched. Not exactly a bedtime image, but don't worry. It's only theoretical and wouldn't happen for tens of billions of years, if ever. Then there's the cyclic universe theory, in which dark energy eventually reverses course and triggers a contraction instead of expansion. The universe shrinks, heats up, and boom, another Big Bang, a cosmic reboot. Some fringe thinkers even suggest that the dark energy we detect is evidence of interaction with parallel universes. Maybe space is leaking energy from a neighboring bubble. Maybe dark energy is the stretch mark of dimensions rubbing together like tectonic plates. Maybe it's none of the above, and we're just grasping at metaphysical fog. One of the more poetic ideas is that dark energy is simply a placeholder for our ignorance. Like the way ancient civilizations once blamed eclipses on angry gods or placed stars in fixed crystal domes, maybe we've just given a mysterious phenomenon a name, so we don't have to lie awake at night wondering how much we still don't know. But you are lying awake, aren't you? Comfortably so, because somehow even the uncertainty has become part of the beauty. It's okay not to know. The not knowing leaves room for wonder, and in that space, your imagination becomes as vast as the cosmos itself. A curious fact, Einstein's cosmological constant, the term he originally invented to keep the universe static, fits neatly into the equations describing dark energy. He abandoned it after learning the universe was expanding, calling it his greatest blunder. But now, that very same constant might be the best mathematical tool we have for explaining this acceleration. One physicist's discarded doodle might end up being the code that describes the end of time. And so here we are, floating in a universe ruled not by what we can see, but by what we can't. Dark energy pulls the strings, expanding the stage, stretching the curtain. It's the silent partner in the cosmic duet. No one knows its origin, its substance, or its fate, but its effects are undeniable. As you ease towards sleep, picture the galaxies as tiny boats, each drifting apart on a tide we cannot feel, pushed by winds we cannot see. They don't struggle, they just go. And you, in your tiny corner of one galaxy, can feel the peace of that gentle drift, the quiet inevitability of expansion, the soft push of mystery carrying you forward into the dark. Tomorrow, we'll entertain the strangest idea yet, that universes might bud and pop like cosmic soap bubbles in a frothy bath of reality. But for now, close your eyes and let dark energy do what it does best. Stretch the silence, lengthen the night, and lull you into deeper dreams. By now you're drifting so far into the cosmic unknown that even familiar mysteries, dark energy, horizons, geometry feel like old friends. But tonight, the universe gets even stranger, like it's flipping through channels, showing you brief flashes of other worlds, other beginnings, other laws entirely. You've passed the observable edge, past the redshifted galaxies and fatting starlight, and now you're floating in theoretical space, where the fabric of reality might just be frothing. Yes, frothing with universes. Welcome to the slippery, soapy world of cosmic bubble theory. It begins with a question. If the Big Bang created our universe, could others have formed elsewhere? Not in our space, but in separate, disconnected realms, each with its own Big Bang, its own spacetime, its own physics. That's the premise of bubble universes, one of the more provocative offshoots of the inflation theory we brushed against earlier. According to this idea, inflation didn't happen once and then stop. No, it might be eternal, ongoing, always bubbling somewhere. Imagine an infinite field, a kind of high-energy vacuum still inflating, stretching, silent. Within this cosmic field, little patches occasionally decay into lower energy states. When that happens, a bubble universe nucleates like a droplet forming in a pot of boiling water. Pop, one universe, then another. Pop, pop, infinite pops, each creating a self-contained universe expanding with its own internal laws and constants. This is eternal inflation, but now it's dressed up in a bubble bath metaphor. And honestly, your brain kind of loves it. Historians still argue whether this model is science fiction, or somewhere in between. It's incredibly difficult to test. After all, each bubble is causally disconnected from the others, meaning light, information, even the laws of physics from one universe can't bleed into another. You can't send a probe to the next bubble over. You can't even tell if it exists. But the math says it's plausible. Some of the most respected physicists in the world believe it. And hey, if you're going to drift through space at bedtime, why not drift across an endless, bubbling multiverse? In some versions of this model, our universe is like a bubble slowly growing inside a still inflating field. The bubble wall itself could be moving at nearly the speed of light, expanding into the inflating outside as new space appears. You're not in the center of that bubble, of course. There is no center. There's just space stretching outward and more bubbles popping off somewhere in the unreachable distance. And here's the part that might really tuck you into your pillow: collisions. Some theorists propose that if two bubble universes expand into each other's territory, they might actually collide. Not like billiard balls, but like soft waves meeting and rippling through spacetime. Such a collision could theoretically leave behind a kind of bruise, an asymmetry or anomaly in the cosmic microwave background. In fact, teams have looked for such marks. A few suspicious patches have appeared, like slightly discolored spots on the universe's baby photo. Are they evidence of bubble collisions, or just statistical hiccups in the data? Scientists aren't sure, but they haven't ruled it out either. There's something both thrilling and humbling about that. The idea that our entire observable universe, all 93 billion light-years across, might be just one little soap bubble among countless others. Maybe there's a universe where gravity is stronger and stars collapse into black holes within moments. Maybe another where light doesn't exist at all. Or maybe one where cats actually do rule the cosmos, complete with planetary scratching posts and meteor litter boxes. The point is, if bubble universes are real, then anything not forbidden by physics could happen somewhere. You are one possibility among infinite ones. It also makes the fine-tuning of our universe more intriguing. All the constants that seem suspiciously well-suited to life, gravity, electromagnetism, nuclear forces, don't have to be uniquely magical. If you've got a trillion universes, odds are one of them will get everything just right. We're not lucky, we're inevitable. In this model, the anthropic principle isn't arrogance, it's math. But don't worry, you're not about to bounce into another bubble. The boundaries of your universe are secure, even if they're theoretical. The walls of this cosmic soap bubble expand too quickly for anything to get in or out. You're safe inside your little patch of spacetime, free to drift, dream, and wonder without bumping into another set of physics. Still, it does make you wonder. If other bubbles exist, are they lonely too? Do they have stars? Are they hot or cold, curved or flat, finite or infinite? You'll never know, and that's okay. Some truths are beautiful precisely because they remain just out of reach. like a dream you almost remember or a star whose light will never arrive. A fun little fringe theory. Some physicists believe that the universe we call real might just be one bubble in a quantum foam that's constantly seething with short-lived baby universes. These virtual universes might pop into existence and vanish before time can register them. Like tiny fireworks in a vacuum. It's speculative, yes, but it underscores a larger point. Space, even at its emptiest, is never still, never silent. Even nothingness sees. So tonight, you're floating not in emptiness, but in a foam of possibility. Each bubble expanding, shimmering, unseen. Yours happens to be the one with Beethoven and bad traffic and moonlight and microwaves. It's not perfect, but it's yours. A quiet pocket of physics just stable enough to allow for thought, sleep, and curiosity. Tomorrow, we'll return to more grounded questions about space itself, like whether it has an edge or is simply its own enclosure. But tonight, let the bubbles rise around you. Let the universes pop softly in the distance, and let your dreams drift not just across space, but between the spaces where other worlds might quietly float. You're floating now in the gentle fizz of possibility, bubbles of universe behind you stretching in every direction, each one like a whisper from physics. But here, in your own universe, things are starting to take shape again. Familiar stars glimmer in the dark, galaxies swirl patiently in the distance, and the question, does space have an edge, floats to the surface like a message in a bottle. You open it slowly, and the message is surprisingly vague. The truth is, space may not have an edge at all. That's not because it's infinite, although it might be, and it's not because we haven't found one, though we haven't. It's because the universe might be edgeless by design, not just practically, but fundamentally. That's a very different thing from being infinite. A universe can be finite in size and still have no boundaries, no ends, no walls, no cosmic, here be dragons signs. That's the strange beauty of curved geometry. To help you visualize, picture the surface of Earth again. You can walk in any direction indefinitely and you'll never fall off. You'll just loop back around. The Earth is finite, but it has no edge. Now add a dimension. Imagine that our three-dimensional space curves in a similar way, not across a surface, but in itself. That's a closed universe. It could be the shape of a hypersphere or something even more exotic. You could travel in a straight line forever and eventually end up back where you started, assuming you had a few trillion years and a really durable spaceship. But the universe doesn't have to be closed. It could be flat or open, stretching infinitely in all directions, a vast plane with no curvature and no boundary. Not because it wraps around, but because it never ends. It's like asking where the edge of a number line is. There isn't one. You just keep counting. Space might be like that, endless, seamless, and frustratingly resistant to giving us a clean edge to find. Historians still argue whether the universe is truly infinite or just unmeasurably vast. Current data from the cosmic microwave background tells us that space is flat with only a tiny margin of error. But flatness doesn't necessarily mean infinite. It might just mean that the curve is too gentle for us to detect, like standing on an enormous sphere and insisting it's flat because the ground looks level. And here, where things get fun, topologists, mathematicians who study the properties of space, have shown that you can have a flat universe that still loops. Just like in video games, where running off the screen on the right brings you back from the left, space could be multiply connected. You could fly off in one direction and after enough time and distance, see the back of your own spaceship. The universe could be a cosmic hall of mirrors with light looping through it endlessly. Of course, we've looked for that. Scientists have searched the sky for duplicate images of galaxies, patterns in the cosmic background that repeat, clues that light has wrapped around the universe. So far, nothing conclusive. But the possibility remains. Space might be finite and edgeless, just too big and subtle for us to notice the loop. There's also the philosophical question. What would an edge even mean? If you could find the end of space, what lies beyond it? More space? Nothingness? Something else entirely? If you reached the edge, could you touch it, pass through it, or would physics itself break down in protest? The truth is, an edge makes sense on paper, but not in the universe we live in. In cosmology, edges tend to cause more problems than they solve. They require strange boundary conditions, unexplained transitions, and a lot of unsatisfying hand-waving. Instead, most cosmologists lean toward a boundaryless model, not because it's easier, but because it works. It fits the math, it fits the data, and it gently tucks us into a universe that doesn't need a border to be complete. Still, a few fringe thinkers propose scenarios where space does end, just not in the way we imagine. Some quantum gravity models suggest that beyond a certain scale, space itself dissolves into something more fundamental, like pixels on a screen or strings in a deeper dimensional fabric. In these models, the edge of space isn't a place, but a threshold, where classical geometry stops working and something stranger takes over. Then there's the simulation hypothesis, a philosophical curveball suggesting that our universe is a digital construct, and the edge is just the limit of the rendered environment. You've heard this idea before, and it sounds like sci-fi, but it raises a valid point. If space is a construct, either mathematical or computational, then it has rules. It has bounds. And those bounds might show themselves in strange patterns, like cosmic speed limits, quantized space, or subtle symmetries that hint at something hidden. But before you start poking the air expecting glitching pixels, breathe. Simulation or not, your universe is astonishing. Whether space is endless or finite, looped or flat, it holds galaxies, stars, and soft little planets where things like you can wonder about its shape. That in itself is incredible. Here's a grounding thought to end with. You may never find the edge, but you don't need to. You already live inside the miracle. You are surrounded on all sides by something vast, ancient, and deeply mysterious. And it's holding you gently in place with no walls, no cages, and no instructions to leave. So as you curl deeper into the night, feel the edgelessness of it all, not in a dizzying way, but in a peaceful one. You are not perched on the brink of space. You are swimming in it. You are folded into the fabric, wrapped in the subtle geometry of existence. And whatever the shape of that geometry, whatever the size of your cosmic enclosure, you belong here. No edge needed. The night has grown long now, and so has your journey. You've drifted through the curved folds of spacetime, past bubbles and boundaries that may not exist, through dimensions that may wrap or stretch or shimmer. But now the universe around you feels different, quieter, older. Tonight you float into a future so distant, so gently disassembled that even the stars begin to fade. This is the slow decline, the final breath, the ultimate lullaby of the cosmos. Tonight you arrive at the idea of heat death, a universe that doesn't end with a bang or a crunch, but with a sigh, a whimper, a long and fatting hush. First, let's get one thing clear. Heat death sounds dramatic, but it's not about burning, it's about balance, or more precisely, equilibrium. The idea comes from thermodynamics, specifically the second law, which says that entropy in a closed system always increases. Entropy is the tendency toward disorder or randomness, and in cosmology it plays the role of the universe's silent metronome. Left alone, everything trends toward evenness. Hot things cool, dense things spread out, and energy flows until there's no useful difference left. In other words, everything settles. Right now, our universe is busy. Stars are burning, galaxies are dancing, planets are circling suns, and light is zipping across space. But none of this will last forever. Over trillions of years, stars will burn out. New stars will form, yes, but more and more hydrogen will be used up. Galaxies will grow old. The night sky will darken. Eventually, all that remains will be the remnants, white dwarfs, neutron stars, and black holes, silent, dense, and drifting. Then even those begin to vanish. Over unimaginably long stretches of time, far longer than the age of the universe so far, black holes will evaporate via Hawking radiation, a process so slow it makes glaciers look speedy. One by one, even the most permanent structures of space will fade away. And what's left? Nothing, but not the nothing you might be thinking of. Not a void, not a vacuum that's empty. What remains is a state of perfect thermodynamic equilibrium, a universe where everything is the same temperature, the same energy level, the same everything. No differences, no gradients, no movement. No work can be done because doing work requires imbalance, and imbalance is gone. This, according to most current models, is the end game. A cosmos that is eternally cold, eternally dark, eternally quiet. The heat death of the universe. Historians still argue whether this is inevitable or if there's a twist waiting somewhere deep in the equations. Maybe dark energy will reverse or quantum fluctuations will trigger a rebirth. But based on what we know now, heat death seems not only possible but likely. The universe doesn't die in a cataclysm. It doesn't collapse. It doesn't explode. It simply runs out. A fringe theory offers a slightly spicier take. In the deep future, random quantum fluctuations might spawn pockets of order, perhaps even brief, accidental observers, sometimes called Boltzmann brains. These hypothetical entities pop into existence, fully formed, just long enough to think a thought before dissolving. It's a deeply unsettling idea and not widely accepted, but it underscores the profound weirdness of a high-entropy universe. Even randomness can create islands of meaning briefly. Here's a comforting twist, though. This won't happen tomorrow, or next year, or in the next trillion years. The universe still has plenty of activity left. Stars will continue to burn for billions of years. Planets will spin, black holes will feed, galaxies will drift. It's only in the very distant future that this great stillness arrives. If you had a cosmic calendar, heat death wouldn't even be on the last page. It would be in the fine print at the back, written in invisible ink. Still, there's something profoundly poetic about it. The universe, born in a blinding burst of creation, will end not with violence but with quiet. The same laws that allow stars to shine and galaxies to spin also demand that everything will eventually rest. It's not a punishment. It's not failure. It's just balance. And maybe that's the most peaceful idea of all. The cosmos doesn't go out fighting. It doesn't rage against the dying of the light. It simply completes its cycle. Creation, complexity, stillness. You might wonder what happens to time in a universe like that. If nothing changes, does time still flow? If there's no movement, no contrast, no before and after, what does time even mean? Some physicists suggest that in such a universe, time becomes irrelevant, a frozen ocean rather than a moving river. But that's a mystery for another night. For now, rest in the hush. Picture a sky with no stars, a universe where everything is spread so thin that collisions are impossible, where even particles rarely meet. A quiet so complete it hums, not empty, just done. It may sound bleak, but think of it this way. You are here now during the golden age of the cosmos. You live in a time of stars and warmth and possibility. The universe is still singing, still stretching, still glowing. That in itself is miraculous. So as you close your eyes and drift deeper, let the silence of future space wash gently over your thoughts. No panic, no rush, just the slow, inevitable settling of everything into rest. Tomorrow, we'll wonder whether any of this is even real, or if we might be dreaming inside a cosmic simulation. But tonight, let yourself ease into the soft ending of all things, not with fear, but with peace. Let the universe exhale. Let yourself fade gently into its quiet rhythm. You've followed the universe into its twilight, stars dimming, galaxies stretching apart, heat fatting into equilibrium. But just as you begin to accept the hush, another idea tugs at your sleeve. One so strange, so delightfully provocative, it makes all the cosmic expansion, curved space, and dark energy feel oddly quaint. What if none of this is real? What if space isn't expanding because of some unknown force, but because someone or something coded it that way? Tonight, you take a dreamy dive into the shimmering rabbit hole of the simulation hypothesis. Let's set the stage gently. The idea isn't new. Philosophers have toyed with versions of this for centuries. Plato's cave imagined people seeing only shadows of reality cast on a wall. Descartes worried that an evil demon might be feeding him false sensations. But in the early 2000s, philosopher Nick Bostrom upgraded the concept for the digital age. If it's possible to simulate a universe, complete with conscious beings, then it might be likely that we already live inside one. And here's why. Suppose future civilizations develop computers powerful enough to simulate entire worlds, complete with physics, consciousness, and cat videos. If even one such civilization exists, they might create countless simulations, running ancestor histories, exploring different versions of reality, or simply entertaining themselves. The logic goes, if simulated universes far outnumber real ones, what are the odds that you happen to be in the real one? That, my sleepy traveler, is the heart of the simulation argument. You might be picturing a blinking supercomputer floating in space, cables like tentacles, screens filled with stars. Or maybe a lonely programmer sipping cold coffee while adjusting gravity sliders on their lunch break. But the truth is, we don't know what the host reality would look like, or even if it obeys anything resembling our physics. All we know is that if it's possible to build simulated universes and run them well enough that the conscious beings inside don't suspect it, then it becomes hard to rule out the possibility that we are among them. So what would the evidence look like? Is there a cosmic glitch in the matrix? Some pixelated edge to reality? Surprisingly, physicists have speculated about that too. Some suggest that the universe's apparent digitality, the quantization of energy, the discrete nature of particles, might hint at an underlying code. The Planck length, the smallest measurable unit of space, could be a kind of resolution limit, like the smallest pixel on a cosmic screen. Others point to the universe's finely tuned constants. Gravity, electromagnetism, the strong and weak nuclear forces, all balanced just so to allow stars to form, atoms to bond, and people to wonder. Is that chance? Or was it configured? Some even suggest that the speed of light is a kind of cosmic frame rate, an upper limit hardwired into the simulation's rules to prevent computational overload. Clever, right? Historians still argue whether any of this is meaningful or just clever coincidence. Most physicists agree we have no conclusive way to test the hypothesis. If the simulation is well made, after all, it wouldn't leave evidence. It would mask its own code, just like a good video game hides its rendering engine from the player. You don't see the wireframes behind your couch or the algorithms behind your reflection. Why should the universe be any different? But even the lack of testability hasn't stopped people from playing with the idea. Elon Musk famously claimed there's a 1 in billions chance we're living in base reality. Others, more cautiously, call it a useful metaphor for the weirdness of quantum mechanics and cosmological fine-tuning. And yes, there are some fringe thinkers who take it even further, suggesting that déjà vu, psychic experiences, or strange dreams might be code updates or memory wipes. Entertaining, sure. Provable. Not really, but fun to think about when the lights are low and your brain starts to wander. A quirky detail that's floated through philosophical circles. If you believe the simulation theory is true, and the simulators might be watching for interesting outcomes, then speculating about the simulation might actually draw their attention. In other words, you're pinging the gods by thinking about them. Cheeky, maybe even brave. So if your lamp flickers or your dog starts speaking Latin in the middle of the night, maybe say thanks. But even without glitches, the idea carries weight. If you are in a simulation, does that make your life less meaningful? Or more? After all, everything you feel is still felt. Every thought, every emotion, every quiet wonder as you lie in bed listening to the universe breathe, it's all real to you. And maybe that's what matters. Whether atoms or algorithms, you exist. Your experiences echo through a world shaped by rules, whether natural or written. The simulation idea also casts a poetic light on your journey so far. The expanding universe, the cosmic microwave background, dark energy, heat, death, they're not less impressive if they're simulated. In fact, if someone coded all that, they're really good at their job. You're living in an elegant masterpiece, one with stars that birth elements, black holes that stretch space, and minds that wonder where it all came from. Or perhaps this is base reality after all. Perhaps no simulation could ever capture the subtlety of a falling leaf or the ache behind a memory. Maybe reality, as messy and mysterious as it is simply too rich to fake. Maybe you're here because this is the one true universe, unfolding naturally from the Big Bang to the end of time. But even if you're not, that's okay. The point is, you're here now, in this moment, drifting gently in the possibility that everything around you is part of a vast experiment, a digital dream, or an intricate simulation that loves its story too much to let it go. Tomorrow, we'll return to the stars, not to ask what the universe is, but to imagine who might be out there exploring it alongside us, now or in the deep future. But for tonight, let this idea cradle you like a softly humming hard drive. Let your breath settle into the rhythm of a well-rendered world. Close your eyes and fall asleep in a universe that might be dreamed, but feels real and warm and yours. By now you've floated through the soft glow of ancient photons, curved through invisible geometries, and brushed up against the possibility that reality itself is a simulation. And yet, somewhere in all that cosmic abstraction, a very human question remains. What comes next? Not for stars or galaxies, but for us. Tonight, we look ahead, not to the end of the universe, but to its future explorers. Because as long as humans exist, we look outward. So, as you sink deeper into your pillow, let's imagine those who will one day chase the edge of space. For all our modern technology, we're still clinging to a small rock orbiting an average star in a relatively quiet part of one spiral galaxy. But humans have always been restless. We crossed oceans in wooden boats, radioed across continents, landed rovers on Mars. The same curiosity that once led us to map Earth will someday push our distant descendants into the stars. But what kind of universe will they inherit? By then, the expansion will have continued. Galaxies we see today may have redshifted beyond detection. Space will have grown larger. The cosmic horizon will have shifted further. And yet those future explorers, descendants of humanity, or maybe something we've become, will still chase it. Because they'll carry the same spark you do, that urge to ask what's out there. They might not look like us. Evolution doesn't stand still, and technology shapes biology. Maybe they'll be post-biological, minds uploaded into artificial carriers, spacecraft the size of cities or neurons, thinking in symphonies of logic and light. Maybe they'll be engineered to thrive in radiation, ice, and vacuum. Or maybe, just maybe, they'll still wear suits, helmets fogged with breath, hearts beating a little faster as they step onto alien soil. And their mission, to explore, to observe, maybe to understand the structure of the universe from a new perspective. If space has no edge, they'll map it anyway. If the universe keeps expanding, they'll chase the galaxies as long as physics allows. Even if they know they can't reach the end, they'll try, because the act of reaching matters. A curious possibility arises here. Future civilizations might build cosmic observatories, not on planets, but across entire solar systems, tuning massive arrays to detect the faintest traces of galaxies slipping over the horizon. They may even create simulations of past skies, reconstructing the lost light of vanished stars. After all, with enough computing power, you could simulate portions of the observable universe, restoring what the dark energy has stolen. Historians still argue whether that's optimism or nostalgia, trying to digitally recreate the sky of a younger cosmos. But it might be the only way to study the parts of the universe that have disappeared beyond reach, to remember what was, in order to better understand what remains. Fringe thinkers propose more adventurous possibilities. What if those future beings learn to manipulate dark energy? What if they can slow expansion or open wormholes, bridges across vast distances, shortcuts through the stretching cosmos? It's pure speculation, of course, but not entirely forbidden by physics. Some models allow for exotic matter that could keep a wormhole stable. Others suggest space itself could be engineered, curved intentionally to create new pathways. Maybe these distant explorers will learn to leave our bubble entirely, hopping from one universe to another, like a cosmic version of island hopping. Or maybe they'll send signals instead, carefully crafted messages, encoded in gravitational waves or quantum entanglement, reaching out to neighbors they'll never meet. And what would they say? What does a civilization 1 trillion years old send into the dark? Not coordinates, not instructions, maybe something more poetic, a math-based melody, a map of dreams, or just a pulse of light repeating the message, "We are still here." Here's a comforting detail. Some physicists believe that black holes could one day serve as libraries. As the rest of the universe dims, advanced beings might use black holes as data storage, encoding vast amounts of information in the fine details of their event horizons, perhaps even consciousness itself. Imagine a future where everything once known, every poem, every equation, every moment of joy and curiosity, is preserved not in books, but in the gravitational ripples of a fading star. These explorers, then, aren't just seeking answers. They're archiving meaning, holding on to the memory of the universe while it's still bright enough to remember. Of course, some things they'll never reach. The true edge of space, if it exists, might always remain beyond them, just as it does for you. But that's okay. Exploration isn't about reaching the finish line. It's about the journey, the striving, the fact that somewhere in this vast and expanding cosmos, life rose up and cared enough to wonder. You, lying here tonight, wondering if space ends, are already part of that legacy. Your thoughts, your curiosity, your gentle awe under the stars. It's all part of the same thread that will one day lead descendants to the rim of known space, and maybe beyond. So picture them, not alone, but woven into a lineage that includes you. Your bedtime questions, your stargazing moments, your quiet, open-hearted wonder, it matters. It echoes. Tomorrow night, we'll return to the beginning of the question, full circle. We'll rest in the mystery of infinity itself. But tonight, feel the future quietly unfolding. The spacecraft leaving new footprints, the telescopes peering into the red-tinged dark, the explorers whispering your question as they cross yet another light year. And as you drift into sleep, remember, the edge of space might never be found, but the search for it, the endless, elegant search, is where the real adventure lies. And now, here you are, floating on the last ripple of this long, stardusted tide of thought. You've drifted with the ancients beneath celestial domes, rode spirals through Newton's infinite expanse, curved spacetime with Einstein, stretched it with dark energy, and peered into cosmic foam brimming with bubbles. You've watched galaxies redshift into silence, listened for echoes of other universes, and imagined futures far beyond your reach. But now, softly, the central question curls around you one last time like a familiar blanket. Does space end? It's the kind of question that sounds simple when whispered in a dark room, like asking if a road ends or if the sky has a ceiling. But after 20 nights of slow exploration, you understand just how tangled that question really is. Space doesn't end in a brick wall. It doesn't stop like a movie that reaches its credits. If it has boundaries, they're not physical, they're conceptual, mathematical, philosophical, maybe even emotional. Current cosmology suggests space has no edge. It might go on forever, infinitely expanding. Or it might be finite, looping back on itself in dimensions you can't perceive. But either way, it isn't about hitting the end. It's about what can be seen, known, touched, or reached. The visible universe, vast as it is only a sliver, an ember in a fire you'll never see completely, a page in a book with infinite chapters. And yet the human mind presses outward. We ask not because we expect an answer, but because something inside us leans toward the infinite. It's a quiet defiance against our limits, a refusal to accept just enough. You are the species that looked at the moon and thought, we should go there. That stared at deep sky photos and asked, what's beyond those galaxies? That built particle accelerators, peered into Planck-scale phenomena, and imagined realities where logic folds in on itself. Does space end? The best answer science can give you right now is, we don't know, and it might not even be the right question. Space may be edge-free by nature, curved in ways that make edges obsolete, like asking where a circle begins. But the fact that you're asking, that you're lying there, wrapped in darkness, reaching outward with your thoughts, that is extraordinary. Historians still argue whether the concept of infinity came from a mathematical need or a spiritual longing. Maybe both. Infinity is unnerving. It mocks our tidy categories, laughs at closure, resists resolution. But it also comforts, because an infinite universe means there's always more to see, more to learn, more places for minds and matter to unfold. Fringe theories flirt with playful ideas, that the universe is a hologram projected from a distant boundary, that it's a bubble in a higher dimensional space, that what we call space is just a strange form of information, stitched together by entanglement. Maybe the question of edges is like asking where a dream ends, at the pillow or in the final breath before waking. And maybe it doesn't matter, because what matters is what happens inside the space. Inside you, your awareness, your questions, your brief moment of presence in an expanding cosmos. You are not lost in the void. You are the observer, the one asking. You give shape to the space just by noticing it. You turn cold vacuum into meaning, numbers into narratives. You are the poet tucked inside the particle, the wanderer inside the wave. Even if space doesn't end, your perception of it does. That's the beautiful limit. Your horizon is emotional as much as physical, and that's why stories like this one matter, why science and sleep can share a bed. They both stretch you softly. They carry you further than your feet could ever walk. And now, as the stars go quiet and the sky folds in, you're not looking for the edge anymore. You're resting in it, floating on the unknown, at peace with not knowing. So here is your answer, not in numbers but in feeling. Space doesn't end. It just continues, through starlight and silence, through particles and possibilities. It continues in every direction and in every thought you send into the dark. And you continue too. Now rest,